So hello and welcome friends to our channel Intro Mech, and here we discuss about basic mechanical engineering concepts. So today's topic is about motors. So we know that motors are widely used in many applications. You can see on the screen whether it is a conveyor or a indexer or say just pulley drive. So in various applications the main driving system is your motor. So it is very important to select the motor properly, because there are a lot of different types of motors available, and according to the application we have to select the motor. But before that, we should know that what are the motor sizing parameters. That means when we go to catalog of some motor, which parameters are required to see in the chart. So unless and until we calculate or we know these parameters, we cannot select the motor properly. So our today's session is based on the same thing, that how we can calculate the motor sizing parameters uh, online. That means, is there any tool which is readily available? So yes, and we are going to look the same tool. So without wasting time, let's get started. So here is our application. So we have a small indexer and four pieces are placed over here, and we want to rotate this table, right? So we want to rotate this indexer. So what do we have? We have an additional mass, we have a indexer table here, right? And then we have a driving shaft, we have bearings for the support, then we have a motor to drive this system, and essentially we require some gearbox if our output speed is very less. So in that case we have to put a gearbox in between uh, after the motor, right? So let's see what are the different types of motor, right? So the main first question arises that which type of motor is should be used for this application. You can see here there are AC motors, DC motors, then special motors. Again in AC motor there are different types, then DC motor there are various types, and the special motors we know the stepper and servos and all that. So first we should study about general basic things of these motors, that how much power and how much RPM and how much torque these motors give, and what are the special motors. Because based on our application, if we require very high accuracy, then which type of motor should be used, because there are gearing system in the motors also, so there is a backlash. So on the basis of accuracy and all other parameters we should select this motor. But while selecting this any type of motor, we require some input parameters. So our session is based on how we can get those parameters. Now here in our application, how we can get the input parameters and what are those input parameters, let's see. So for the motor sizing, the most important three parameters are: first one is moment of inertia, then the torque and the speed. Now most of the times it happens that we neglect this moment of inertia, we just focus on speed torque relations, and sometimes it creates problem, because we have to check the moment of inertia, the ratio which is mentioned in the motor catalog, because we have some load which is say rotating, so it has its moment of inertia. So whether the motor is can take this moment of inertia or not, so that is required to be checked. So these three parameters are important. Now how we can calculate all these three parameters in our system for our application, so that is the question. So if you go for hand calculations, it can take a lot of time. So let's see the tool which is readily available. So just go on to the Oriental motor sizing tool, type that, and you can see here the motor sizing calculations, the orientalmotor.com. So go on to that site. So here you can see the front page, the motor sizing, and they have mentioned uh, the different parameters. The different motors are given here: servos and AC, brushless DC, linear actuators, and all other parameters are mentioned over here. The motor sizing, you can see here the selection procedure. What is the selection procedure? What are the parameters? You can see dimension and mass, density of the load, dimension and mass of each part which is placed onto the part, then resolution, accuracy, whether we require holding, whether we require brake. So all these input parameters are required, and then motor sizing calculations. So what are we looking for? The three main parameters like moment of inertia, the torque, and the speed. So they have given what is say moment of inertia, the basics. You can read out these things. What is torque, how it varies application to application. So these things are very important, and according to the configuration of your system these parameters vary. So you just cannot apply the same formula to each system, and that's why this tool is important, because it offers a wide range of things, right? So click on motor sizing tool here. So let's click. So after clicking on the motor sizing tool, one window will open here, and here now you can see the applications, different applications like ball and lead screw, then there is index table, then belt actuator or a conveyor arm, a rotary device. So these different applications are mentioned over here. So we know that our application is like index table, right? So we will go for the index table and we will see what kind of data we have to input over there so that we can get the output, right? So now you can see here the index table. They have also mentioned the meaning of all the things on the site properly, so that while entering the data we should enter the correct data, right? So initially the unit system, that is very important. So it is driven by the belt drive they have mentioned. In our case there is a direct drive, so there are different options available. First we will select the metric system, right? Then we have a table shape and dimension. So our table is round, we know. So what data is required? Diameter and thickness, right? So let's put our table diameter here. So as soon as you put on the round table, the rectangular plate dimensions will get removed. So what is our diameter? Let's assume the diameter say 300 mm. So that is our disc, which is like 1 feet, right? So mass, you have two options. You can directly put the mass, or you can put the thickness and the material. It will automatically calculate the mass. So let's say 12 mm thickness and steel is the material. So mass option will get discarded because it will automatically calculate the mass, right? So let's move to next thing, the drive shaft dimensions. So we have some bearing housing and the driving shaft, right? So we have to put the driving shaft diameter over here. So let's say our driving shaft diameter is let's say 40 mm, right? Then again we have a shaft mass option. We can put a length and density, it will automatically calculates. So let's say the length of our shaft is like say 200 mm, right? And the density is the material is steel, right? So next we have load shape and dimension. Now we have placed 4 cylindrical loads on the table, right? So there are different options. If there is no load, we can have a no additional load, but we have cylindrical type, so we will go for a cylindrical type. So we will put the diameter, load diameter of those cylindrical parts over here. So let's say the diameter is a 50 mm, and then the distance from the table center to the load center, that means at what radius we have placed those cylindrical parts, right? So that is important. So let's say those are placed at 175 from the center, right? Then there are number of loads. We have four number of loads, right? And mass of the load, we will put the height and again the load material. So let's say the height is 100 mm and the parts are of aluminum, right? We are considering the aluminum as a material over here, so it will calculate its mass automatically into the system. Then we have a table support. If you are not giving the table support, we don't consider this option, but generally we give the support. There is a bearing housing below the indexer table which takes care of the there are deflections in the shaft, there are deflection on the table, so the support is required. So that's why generally there is a bearing housing is provided for such kind of application. So we will go with the same. We will select the second type. We are not supporting on below the table, but we are giving the bearings to the shaft. So we will go for the second option. And let's consider the coefficient of friction for this application. So we have to diameter if you use ball bearing, so right, distance from the center to be supporting mechanism, right? So we have to give the distance and size. So let's select the coefficient of friction as 0.1 mm here, and the distance from the center of the shaft, we will have this value as, let's say 60 mm. And then the efficiency of the system, let's consider it as a 75 mm because there are mechanical components and all that, so efficiency should be considered. Now here we are considering in our application it is a direct drive, so we are not going to put the belt inputs. Our application is horizontal. Then other requirements, it is necessary to hold the load even after the power supply is turned off. In our application we are not going for that. And the second option which is given as, it is necessary to hold the load after the motor is stopped. So yes, we require that. So with this we will require a brake motor, so we will take that option because the load should be stopped at that moment, right? That is our requirement. So then we have operating conditions, that how much speed the indexer is rotating. We will go for fixed speed operation, right? So it will ask you for the operating speed and the acceleration. So operating speed and all these parameters are dependent on your cycle time. So let's put the operating speed a little bit lesser. So this value is totally dependent on your application. So let's put this v1 speed as a 5 rpm. The speed is little bit slower, so it is like say 5 rpm. And then the acceleration time, so we will select this acceleration time as lesser, because on this acceleration time also your cycle time varies, because if the motor takes more time to accelerate to that position, your cycle time can vary. So let's select the acceleration and deceleration time of the motor as say 1 second. So let's reduce that to 0.5 seconds. So we are going for 0.5 second, right? And then we have a stopping accuracy option, right? So this option is very important, that how much accuracy you require. Like I said, there is a backlash in the system, so the part will not stop at its location. It is rotating, and when the motor suddenly stops, it can move like forward. So if it moves forward, by how much extent or how much degree it should move, that is acceptable to the system. So that is the meaning of stopping accuracy. So some applications are very precise, they require very precise control. So that's why this parameter is very important, because sometimes uh, this also affects the quality of the system. So again, you can put the stopping accuracy in degrees, or they have given the load center circumference. So we require a very precise application. Let's consider here. So we will put 2 micron stopping accuracy over here, right? So, and then the safety factor, how much safety you require. So that is again dependent on your application, your system, that how much safety you require. So let's select the safety factor. What options we have? Let's see, 1.5, 1.75 and 2. So let's go for a higher end. So we have selected the safety factor as 2. So we have now I think given the input to all the fields, right? So from the start we just give the dimension, table dimensions, then drive dimensions, load shapes and all those things, and support things. So finally there is an option of calculate. So just hit on the calculate, and here are the sizing results. These are the important results for us. We can see here the load inertia, the required speed, the required torque here. So these are the parameters that are required while selecting a sizing a motor, right? The required torque is mentioned over here, because while selecting a motor we will see these parameters in its catalog, but we directly cannot go for that, because here you could see the speed is very less, our motor RPM is very high, so we have to go for a gearbox in between. So it will change some of the parameters. We will see that into the next session, that how the gearbox affect these things, right? So these parameters are very important, and we can see uh, that some tips are given over here at the bottom side. We can see those tips. So let's go for the tips to view the motor selection, because we have now these parameters, right? So as soon as you hit on to the tips, it will pop up a window. So they have given some inputs, like if your motor is say AC motor, so how you can see the parameter. They have given the say torque and the gear ratio. Now you require the gear ratio here. Definitely we will see that into the next session. Then if you go for a DC motor, which parameters are required to be seen here, you could see the so then again there is a stepper motor, some graphs are given, so sometimes we have to pick the value from the graphs also while selecting the code. And here comes the importance of moment of inertia, like rotor inertia they have given, and at bottom the ratio is given. This inertia ratio is very important. Here you could see the load inertia which we have calculated from the system. So that is the importance of that calculation. We have to put that value here, and we have to check that whether the motor ratio, the ratio which we are getting is satisfying the motor inertia ratio or not. So that is the importance of these calculations of these motor sizing parameters, right? So this is how we can calculate all these parameters, because in all the applications it is not possible to calculate all these things, because sometimes the systems are complicated and complex. So and also here you can see the motor, the permissible load inertia is also given. So how much inertia the motor permits, so we can cross verify. And the other considerations like duty cycle and overrun as given here, so you can read more about that. Then the second is stopping accuracy is given, the same thing which we had discussed earlier, the stopping accuracy according to the products they have mentioned. The accuracy is mentioned in arc minute, you can see. So that is the angular distance, and also they have mentioned the degrees here. So according to that also we have to select the motor, because this accuracy also matters. And then they have also mentioned the gear head backlash. So what will be the backlash into the gear head? So they have also mentioned, because when we attach the gearbox, there are gears and it induces the backlash into the system. So that also we have to consider. We can save this file and we can take it as a reference, right? So this is how we have calculated these parameters. And I think you understood the importance of all these parameters and how they are required into the motor selection, and how we can easily calculate these things from this site. We have to compare our system with the available configurations. Over here you can see the different configurations. So it is not necessary to have the same configuration all the time. We can have different configuration. So we have to go for a different system, because all the system will have different inputs. Here you could see we have selected belt actuators, so all the inputs are different. So according to that we have to give the inputs, and then only we can get the actual motor sizing parameters, right? So I think this is all about this Oriental motor sizing tool, and this is freely available. You just have to log in into this site and you can get access to all these data, right? So this is it for today's session. And if you have any sort of doubts and queries, please do write into the comment section and we can discuss over there. Until then, stay home, stay happy, and thank you for the patient listening. Thank you.